This video is all about autocorrelation, but I want to begin by explaining correlation. I'm going to do that by example, and I'm going to rely quite heavily on this concept of expected value. So here we have a plot of data that are positively correlated. So each one of these points represents a single individual. It's got two random variables. First, the height of that individual, and secondly, the weight of that individual. The vertical line shows the expected value or mean value of height, and the horizontal line shows the expected value or mean value of weight. So let's look at individuals that are in this height class. So we're dealing with the folks in a height class that is greater than the average value of height. If we look at the weights of these folks, those weights tend to be greater than the expected value of weight. On the other hand, if we consider folks that are in height class that is less than the expected value of height, and we look at their weights tend to be less than the expected value of weight. So that's an example of positively correlated random variables. Now we can think about uncorrelated random variables, and here we have the age of some adults and their heights. So if we consider people in an age class that is greater than the expected value of age and look at their heights, they tend to be neither higher nor lower than the expected value of height. And similarly, folks that are in an age class that is lesser than the expected value of age tend to have heights that also are not different from the expected value of height. So those are uncorrelated data. Now I want to talk about autocorrelation. Now, with correlation, there were two random variables. For example, height and weight, or age and height. Now there's only going to be a single random variable, uppercase Y, and I'm going to generate a sequence of observed Y values. In the first sequence we're going to generate are going to be uncorrelated values. And the first value in this sequence is going to be obtained by taking the expected value of Y, which is 5.0, and adding a little bit to it from a normal distribution with mean 0 and standard deviation 1. The second value is going to be obtained the same way. Start off with the expected value, add a little bit from a normal distribution with mean 0, standard deviation 1, Y3, Y4, all the way down to Y100 in our sequence. All these values are going to be obtained in exactly the same way. And if I make a plot of those values, so here's n, here's the location in the sequence, and there's our expected value of y, a horizontal line at 5.0, you can see that there's a random scatter around this expected value. And that ought not to be too surprising, because each one of these y values is independent of every other y value. So if this value of y is greater than expectation, well, that should have no effect whatsoever on whether this value of y is greater than expectation. Now what I'm going to do is simulate a positively autocorrelated sequence of y values. And the first y value, y1, is going to be obtained exactly the same way as was the case here. But for y2 and all subsequent values of y in this sequence, things are going to be different. So for y2, begin with the expected value, add a little bit from a normal distribution with mean 0 and standard deviation 1, and then there's going to be this third component that consists of 0.7 times the first residual, where there is the first residual. And then the third value in the sequence, there's the expected value, a little bit from a normal distribution, and then 0.7 times residual 2, where this is residual 2 that includes a bit of residual 1, y4, there's the expected value, there's the bit from the normal distribution, and added to that 0.7 times residual 3, where this is residual 3 that includes a bit of residual 2, this is a bit of residual 2, this, is residual 2 that includes a bit of residual 1. Now what we see when we plot position in the sequence versus the value of y, we have a distinctive pattern. And this distinctive pattern arises because each one of these values inherits a bit of residual from the preceding value. So if y2 is greater than expectation, then very good chance that y3 would be greater than expectation as well. So for example, if you got this value here, it's not surprising that the next value, since this one was below expectation, this one would be as well. But remember, each item in the sequence has this random draw from a normal distribution. So just by chance, might get a few of these folks here that are above 0. As a consequence, the value of y becomes greater than the expected value. It lingers there for a while until perhaps you get a sequence of these things that are less than 0, so the value of y drops below expectation. So if we look at the overall pattern here, you can see that it's kind of these clusters, below, above, below, above, below, or another way to look at it is it's kind of a wave pattern. It's evident. So one thing I want to emphasize that this is only one possible way to generate positively autocorrelated values. There are other ways, but the whole idea is that with these values of y, values are no longer independent of each other, and therefore you get the sort of pattern you see here. Now I want to talk about the concept of lag, which is a really important concept when we're dealing with autocorrelation. So to talk about lag, we're going to have a single random variable y, and we're going to have a sequence of values of that random variable shown here. And this sequence of values was generated using the process shown here that resulted in this chart shown here. And we're going to begin with a lag of 1. So what do we mean by a lag of 1? Well, we're going to start here at the beginning. We're going to have this 5.07, and then because we're dealing with a lag of 1, we're going to jump 1 and get a 5.13. And then we're going to put 5.07 on the x-axis, 5.13 on the y-axis, and that's going to give us this blue dot here. Then what we're going to do is we're going to move the frame over 5.13 with a lag of 1. We're going to jump 1 to get 5.08. So 5.13 goes on the x-axis, 5.08 on the y-axis, and that's going to give us this green dot there. We're going to continue to move the frame from left to the right. We've got this fifth value of 4.75. We've got the sixth value of 4.83. This goes on the x-axis, this goes on the y-axis, and there's that red dot there. So that is a lag of 1. Now what I want to consider is a lag of 7. So in a lag of 7, we begin here, and we jump 1, 2, 3, 4, 5, 6, 7. So 5.07 on the x-axis, 4.78 on the y-axis. That's the green dot. Move the frame over 1 to 5.13, jump 1, 2, 3, 4, 5, 6, 7. 5.13 on the x-axis, 4.98 on the y-axis. That's this red dot. So we're seeing that what happens with a lag of 1, on the x-axis, we've got the nth value, and on the y-axis, we've got the n plus 1th value. So the last value in this sequence is going to have the 500th value on the y-axis and the 499th on the x-axis if we get a sequence of 500 numbers. And here if we have a sequence of 500 numbers, the last one on the y-axis would be 500, and the last one on the x-axis would be the 493rd. So we'd be plotting on the x-axis, we'd have the nth value, and on the y-axis, we would have the nth plus 7th. If we look at these plots, we see quite a big difference between them. Here we've got quite a strong correlation. Here we have essentially no correlation at all. So why is that happening? Well, if we return here and we consider the first value in our sequence and the next value in our sequence, if this one is above its expected value, this one also is likely to be expected to be above its expected value because it's got 0.7 times this residual plus this little normal bit. On the other hand, if we think of the correlation between this value and, let's say, the fourth value, then what's happened is in between them, we've had these three occurrences of normal, and therefore the association between these two is such that even though this one might be above its expected value, that's going to have less effect of this one being above its expected value. And so the common phenomenon is that the amount of autocorrelation decreases with the lag period. And we can see this in our plot of theta, which is from the handedness experiment, is the probability that a randomly selected person would be right-handed. And if we look at autocorrelation, and autocorrelation being a correlation is going to be from -1 to 1.0, that we can see as the lag period increases, the amount of autocorrelation goes down. So, in summary, we began with correlation. And with correlation, we had two random variables, height and weight. And the whole idea was that individuals with heights that were above the expected value would tend to have weights that were also above the expected value. And then we considered autocorrelation, where instead of having two variables, we just had a sequence of one variable. And what we discovered was that with a lag of 1, if this value was above its expected value, then the next value in this sequence would also very likely be above its expected value. However, with a lag of 7, if this one is above its expected value, that may not have very much effect on whether something that's 7 jumps away is going to be above its expected value. So that's just the concept of lag period and autocorrelation as shown through a simulation process.